Section: Introduction. In this section, we explore how large language models, LLMs, achieve impressive results by being pre-trained on extensive text datasets, utilizing significant computational power. Much of the previous research on LLMs has concentrated on what we call scaling laws. These are empirical formulas that help us predict how the performance of a model changes as we adjust factors like the number of floating point operations, flops, the number of model parameters, and the amount of training data. We have found that power law relationships can effectively forecast language modeling loss and, consequently, the performance in downstream tasks. However, these scaling laws often overlook the influence of vocabulary size. For instance, some studies only consider parameters that are not related to vocabulary in their predictive models. This oversight has led to considerable differences in vocabulary sizes among current LLMs. For example, Llama 2-7B uses a vocabulary size of 32,000, while Gemma 7B has a much larger vocabulary of 256,000, even though both models have a similar total number of parameters. This variation prompts us to ask, what is the most efficient vocabulary size for an LLM? The size of the vocabulary significantly impacts performance. We believe that the ideal vocabulary size should strike a balance, not too large and not too small. A larger vocabulary can enhance tokenization efficiency by breaking down sentences into fewer tokens, which is beneficial. It also increases the model's ability to represent a broader range of concepts and subtleties found in the text. However, larger vocabularies can lead to challenges, such as underrepresenting rare tokens, especially when data is limited. Therefore, we need to determine the optimal vocabulary size by considering both the training data and the number of parameters that are not related to vocabulary. In this paper, we argue that the effect of vocabulary on scaling laws has been underestimated, and we aim to quantify this effect to predict the optimal vocabulary size. We start by introducing a normalized loss formulation to allow for fair comparisons across models with different vocabulary sizes. Using this normalized loss function, we analyze and explain why an optimal vocabulary size exists, which is influenced by the available computational resources. To predict the optimal vocabulary size based on a given compute budget, we propose three methods. The first method involves estimating power laws through what we call isoflops. We pre-train models with non-vocabulary parameters ranging from 33 million to 1.13 billion, grouping models that share the same flops but have different vocabulary configurations. We then fit power laws that relate flops to both non-vocabulary and vocabulary parameters, as well as the training data. Our findings indicate that the optimal vocabulary parameters grow according to a power law in relation to the computational budget, but at a slower pace than non-vocabulary parameters. The second method we introduce is a derivative-based estimation. This approach uses the derivative of flops concerning vocabulary size to find the optimal vocabulary size by identifying where this derivative equals 0. The third method involves modifying existing scaling laws to include vocabulary size and fitting this new formula to our models. This allows us to predict the normalized loss function based on both non-vocabulary and vocabulary parameters, as well as the amount of training data. While the first two methods focus on compute optimal scenarios, this third method also helps us identify the optimal vocabulary size when the model parameters are either overtrained or undertrained. Overtraining is a common issue, as seen with Llama 2-7B, which was trained on 2 trillion tokens, far exceeding the compute optimal allocation for a model with 7 billion parameters, which should be around 150 billion tokens. Our analysis shows that the relationship between non-vocabulary parameters and their corresponding optimal vocabulary parameters follows a power law across all our methods. We predict that vocabulary parameters should scale more slowly than non-vocabulary parameters, suggesting a specific relationship where the optimal vocabulary size is proportional to the non-vocabulary parameters raised to a power of approximately 0.83, which is less than 1. Despite these insights, many existing LLMs overlook the significance of vocabulary and allocate fewer vocabulary parameters than our recommendations indicate. We assume that the training data for these models is optimally distributed. However, since several LLMs are trained on much more data than what is optimal, like Llama 2, we believe that the optimal vocabulary sizes would likely be larger than currently estimated. Finally, we validate our predictions using models with 3 billion parameters. We apply our approach to estimate the expected vocabulary size in various scenarios: when training data is insufficient, undertraining; when training data is appropriately scaled with model parameters, compute optimal training; and when training data is excessively abundant, overtraining. Our results demonstrate that models using our suggested vocabulary sizes consistently outperform baseline models that use commonly accepted vocabulary configurations, all while operating under the same FLOPS budget. Our research highlights the often overlooked importance of vocabulary and emphasizes the need to consider vocabulary size, model parameters, and training data together for effective scaling. Section Summary. In this section, we explore the impact of vocabulary size on the performance of large language models, LLMs, and propose methods to determine the compute optimal vocabulary size, which is often overlooked in existing scaling laws. Our analysis reveals that the optimal vocabulary size should grow at a slower rate than non-vocabulary parameters, and that considering vocabulary size alongside model parameters and training data is crucial for effective model scaling. Section Preliminary. In this section, we first introduce a general formulation of a widely used scaling law and then show how we can adjust it to include vocabulary considerations. When we talk about scaling laws, we consider a computational budget, which we denote as C, measured in floating point operations per second, FLOPS. Our objective is to allocate this compute budget optimally between model parameters, represented as N, and the number of training tokens, denoted as D. The loss function we typically use is the language modeling loss, which we can express as the probability of a word given its preceding context and the vocabulary size. Generally, a lower loss indicates better performance of the language model. However, since this loss depends on the vocabulary size, we cannot directly compare language models that have different vocabulary sizes. Therefore, we will propose an adaptation later in this section. To fit scaling laws, we usually need to train various models under different configurations. A common strategy is to select several compute budgets and train models with different values of N and D for each budget to identify the one with the lowest loss, which we refer to as isoflops. By using fitting techniques, we can estimate a function that maps the compute budget to the optimal allocation of N and D. Now, regarding scaling laws with vocabulary, previous research often assumes a fixed vocabulary size, which means we cannot directly apply their scaling laws and evaluation metrics. Thus, we will outline several considerations that enable us to explore vocabulary scaling laws. First, scaling laws typically focus on model parameters, N, and the number of training tokens, D. We will adapt these for our analysis concerning vocabulary size. We break down the total model parameters, N, into two parts: non-vocabulary parameters, N_NV, and vocabulary parameters, N_V. To understand the significance of vocabulary parameters, we isolate them, where N equals N_NV plus N_V. We represent the vocabulary parameters in the output layer as N_V equal to the vocabulary size V multiplied by the embedding dimension D. Notably, to change N_V, we only adjust the vocabulary size V while keeping the embedding dimension D constant based on empirical observations. Second, instead of measuring data in tokens, D, we will measure it in training characters, H. The number of tokens is influenced by the tokenizer's vocabulary, so we need a measurement of data that is independent of vocabulary size. By focusing on training characters, we can better understand how the volume of data impacts performance, regardless of the vocabulary size. Next, we need to connect our findings with existing studies on scaling laws by mapping from training characters, H, to tokens, D. This mapping is determined by the tokenizer's compression ratio, which we can calculate as D divided by H. The more tokens the tokenizer requires to represent H, the larger d will be, indicating less compression. We develop a simple function, f, v, to estimate this ratio based solely on the chosen vocabulary size, v. We find that a quadratic function of the logarithm of v provides accurate predictions. By fitting several tokenizers with v ranging from 1,000 to 1 million, we obtain specific coefficients that allow our function to predict the compression ratio with low error and high accuracy. For all our main experiments, we utilize the byte pair encoding (BPE) algorithm for tokenization. Finally, to fairly evaluate models that vary in vocabulary size, the commonly used language model loss is not suitable. Models with larger vocabularies naturally have higher losses due to the increased number of possible predictions. However, this does not imply that these models are inferior. Therefore, we need to normalize the loss concerning vocabulary size. We reformulate the unigram normalized metric as a loss function. For a sequence of length t, we design the unigram normalized language model loss based on the frequency of each word in the tokenized corpus. This loss reflects the improvement in probability that a context-aware language model provides over a simpler unigram model, allowing us to evaluate the model's effectiveness. The normalized loss remains consistent for a given model with a fixed non-vocabulary component across different vocabulary sizes. The differences in this normalized loss arise from the model's inherent capabilities. Compared to the original loss, the normalized loss is generally smaller and can even be negative due to the inclusion of a negative term based on word frequency. We can also use the average bits per character, BPC, as a vocabulary insensitive loss metric, with the main difference being in how we normalize the values. Since we use the same corpus for each model we train, the two metrics do not differ significantly in our case. Section Summary. In this section, we present a general formulation of scaling laws that optimize the allocation of computational budgets to model parameters and training tokens, while adapting these laws to account for vocabulary size. We also introduce a vocabulary insensitive loss metric to fairly evaluate language models with varying vocabulary sizes, ensuring that performance comparisons are not skewed by the number of vocabulary options. Section Analysis. Why the optimal vocabulary size is bounded by compute. In this section, we analyze why the ideal vocabulary size is limited by our computational resources. Analysis 1. Fixed normalized loss perspective. We estimate the computational requirements, or FLOPs, of a transformer-based language model as approximately 6 times the product of the number of non-vocabulary parameters and vocabulary parameters, multiplied by the hidden size. Here, the total number of parameters is the sum of non-vocabulary and vocabulary parameters. We observe that model performance initially improves with an increase in vocabulary size, but eventually declines. This happens for 2 reasons. 1. When the vocabulary size is small, increasing it enhances the model's ability to tokenize, allowing it to learn more from a fixed number of tokens, which boosts performance. 2. When the vocabulary size becomes very large, the benefits from tokenization diminish, and the model struggles to train the additional parameters effectively due to limited data, resulting in decreased performance. We provide a more detailed explanation in the appendix and illustrate how FLOPs change with vocabulary size in our figures. Analysis 2. Fixed FLOP budget perspective. With a set FLOPs budget, we focus on how vocabulary size affects loss. We establish several fixed FLOP budgets and use models with similar total parameters while varying vocabulary sizes from 4,000 to 96,000. Our findings show that as the FLOPs budget increases, the vocabulary size that minimizes loss also increases. This indicates that with more computational power, large language models can utilize bigger vocabularies to lower loss. However, simply increasing vocabulary size does not always lead to lower loss. For a fixed FLOP budget, we notice that loss decreases with vocabulary size up to a point, after which it starts to rise again, suggesting there is an optimal vocabulary size. This highlights a trade-off between model complexity and computational limits, where excessively large vocabularies can hinder performance. Analysis 3. Parameter growth perspective. Traditionally, we have scaled language model parameters by either increasing the number of layers, depth, or the size of the hidden layers, width. While much research has focused on these methods, current practices often involve expanding both at the same time. This combined approach may overlook important differences in how various parameters benefit from these expansions. Non-vocabulary parameters can gain from both depth and width increases, allowing for more complex representations and broader feature capture. In contrast, vocabulary parameters, which relate to word embeddings and model outputs, are typically limited to a single layer, restricting their growth from depth increases. Their main growth avenue is through width expansion. This difference suggests that to keep growth balanced, we might need to increase vocabulary size alongside depth, ensuring vocabulary parameters grow in line with non-vocabulary parameters. Estimating the optimal vocabulary size. We outline 3 complementary methods to estimate the best vocabulary size. Approach 1. Power laws via isoflops. We categorize our models into 6 groups based on the number of non-vocabulary parameters, ranging from 33 million to 1.13 billion. Within each group, we only change the vocabulary size from 4,000 to 96,000 while keeping the flops budget constant. We assess the normalized loss on a validation dataset. This method helps us determine the optimal distribution of resources among non-vocabulary parameters, vocabulary parameters, and training data for a given flops budget. Setup. For a specific number of vocabulary parameters, we fix the embedding dimension, meaning that as we increase vocabulary size, the number of vocabulary parameters also increases. In our experiments, we uniformly sample training data from various domains in the Slim Pajama dataset, keeping other hyperparameters constant, with more details available in the appendix. Fitting. We identify the data points with the lowest normalized loss for each flop budget, visualizing all runs in our figures. These points represent the optimal allocation of resources among non-vocabulary parameters, vocabulary parameters, and hidden size. We hypothesize that the optimal number of vocabulary parameters follows a power law in relation to the flops, similar to non-vocabulary parameters and training data. Specifically, we express the relationships as equations where the number of non-vocabulary parameters, vocabulary parameters, and hidden size are proportional to the flops raised to certain powers. Since model size and training data should scale together for optimal training, we set the powers for non-vocabulary parameters and hidden size to be equal. To explore more configurations efficiently, we use interpolation across our data points, with implementation details provided in the appendix. Section Summary. In this section, we analyze why the optimal vocabulary size for language models is limited by computational resources, highlighting that performance initially improves with vocabulary size due to better tokenization but eventually declines as the vocabulary grows too large for the available data to support. We also explore how a fixed flops budget influences loss in relation to vocabulary size, revealing a trade-off that suggests an optimal vocabulary exists, and we propose methods to estimate this optimal size based on power laws related to model parameters and training data. Section. Results. In this section, we present our results. In our figure, we show the fitted power laws. The number of non-vocabulary parameters is equal to 0.08 times the flops budget raised to the power of 0.5. The number of vocabulary parameters is equal to 0.2 times the flops budget raised to the power of 0.42, and the height is equal to 6.42 times the flops budget raised to the power of 0.5. Here, the flops budget is represented by the variable c. The low root mean square error and high r-squared values indicate that our fit is strong. With a given flops budget, we can use these relationships to determine the best allocation of non-vocabulary parameters, vocabulary parameters, and height. We also draw several conclusions. 1. Large language models are very demanding in terms of data. We should allocate more computational resources to training data compared to the non-vocabulary parameters. 2. Vocabulary parameters increase in a power law relationship with the FLOPS budget, meaning that as models require more computation, having a larger vocabulary helps them understand a wider variety of text. Therefore, the size of the vocabulary is crucial for scaling. 3. Vocabulary parameters should grow at a slower rate than non-vocabulary parameters. This difference is evident in their power law exponents, where the ratio of the exponent for vocabulary parameters to that for non-vocabulary parameters is less than 1. We believe this is because, once we have a sufficiently rich embedding space from a large vocabulary, it becomes more important to scale the non-vocabulary parameters to capture the complex syntactic and semantic structures of language using transformer blocks. Next, we introduce an alternative method based on derivatives for quick estimation. Previous research typically assumes a fixed compute budget in FLOPS and seeks to minimize loss by optimizing the allocation of model parameters and training tokens. We reverse this approach, inspired by recent studies. Our goal is to find the minimum FLOPS needed to achieve a specific loss through the optimal allocation of vocabulary size. By calculating the minimum point of FLOPS concerning vocabulary size using derivatives, we can estimate the best vocabulary size under the assumption that it can reach a certain loss. The parameters we need can be easily derived from constructing a function of vocabulary size. In theory, as long as we have the non-vocabulary parameters, we can numerically search for the vocabulary size by solving the equation where the derivative of FLOPS with respect to vocabulary size equals 0. More details on this can be found in the appendix. Regarding usage, we note that the optimal vocabulary size should primarily be determined by the normalized loss rather than the compute budget in FLOPS. However, when the compute allocation is close to optimal, the loss shows a power law relationship with the FLOPS budget, as described by the scaling law. This relationship allows us to use FLOPS with optimal allocation as a reliable indicator of how the optimal vocabulary parameters behave as we scale. In practice, we can first identify an empirically optimal vocabulary size in a low-cost scenario, such as determining the compute optimal vocabulary parameters on a smaller model with the same FLOPS budget. Then, we can proportionally scale the optimal vocabulary parameters as we increase the non-vocabulary parameters. Specifically, we derive a set of optimal vocabulary parameters for different non-vocabulary parameters, which we represent as pairs. We then fit the relationship between non-vocabulary and vocabulary parameters using a power law function. This leads us to a scaling equation that relates the two. By combining the scaling factor we obtained from our derivative analysis with the empirical solution from a smaller model, we can estimate the optimal vocabulary size for any larger model without needing extensive parameter searches. We find that the scaling proportion is approximately 0.83 after our fitting. Consistent with our earlier findings, we observe that non-vocabulary parameters should be scaled more rapidly than vocabulary parameters to achieve the best allocation. Section Summary. In this section, we present fitted power laws that describe the optimal allocation of model parameters based on a given FLOPS budget, highlighting that non-vocabulary parameters should be prioritized over vocabulary parameters for effective model training. We also introduce a derivative-based approach to estimate the optimal vocabulary size, emphasizing that it should be determined by normalized loss rather than compute budget, while confirming that non-vocabulary parameters scale faster than vocabulary parameters for optimal performance. Section. Approach 3. Parametric fit of loss formula. In this section, we outline our approach to predicting loss based on specific parameters. We directly estimate the loss using the non-vocabulary parameter, the vocabulary parameter, and the number of training characters. To find the best vocabulary setup, we look for the point where the loss is minimized in relation to the vocabulary size. We create a loss formula that depends on the vocabulary, where the first part represents the normalized loss for an ideal generative process based on the data distribution. The other parts of the formula account for the influence of non-vocabulary parameters, vocabulary parameters, and the amount of training data on the loss. The parameters we learn include E, A1, A2, B, alpha 1, alpha 2, and beta. For our fitting process, we utilize the data points collected from our experiments. We do not limit ourselves to just the points with the lowest loss for each budget of floating point operations, flops, because we aim to predict loss for any combination of the non-vocabulary and vocabulary parameters along with the height of the model. We impose a constraint that alpha 1 equals beta and filter out points with very low flops. Our fitting results yield specific values for the parameters. A1 is approximately 1.831, A2 is about 0.196, B is around 2.124, E is roughly 5.533, and both alpha 1 and beta are 0.447, while alpha 2 is 0.671. We provide a detailed description of the fitting process in a separate section. Once we have fitted the parameters, we can determine the optimal vocabulary size by identifying the lowest loss concerning the vocabulary size while adhering to the flops budget. For instance, if we know the non-vocabulary parameter and the flops budget, we can substitute a specific expression for the loss and find the solution through numerical methods. We also detail how to compute the derivative of the loss with respect to the vocabulary size in another section. It is important to note that all our proposed methods can be used to optimally allocate the non-vocabulary and vocabulary parameters along with the height of the model. However, our third approach offers more flexibility in predicting the best vocabulary size when the non-vocabulary parameter and height do not follow a specific scaling law. This flexibility arises because our loss formula considers a wider range of combinations of the parameters, not just those that achieve optimal results under a fixed training budget. By keeping the non-vocabulary parameter constant and varying the budget, we can predict the best vocabulary size for different amounts of training data. This characteristic makes our third approach particularly useful, especially since modern large language models often utilize an abundance of training data to create powerful models with lower inference costs. In our analysis, we remove the assumption that parameters and training data are equally scaled, allowing us to predict the best vocabulary parameters. We find that the allocation of vocabulary parameters is often underestimated. When we look at larger models, we report the predicted optimal vocabulary parameters and sizes based on our three approaches, ensuring that the training data is allocated effectively. Our findings indicate that the non-vocabulary parameter should be scaled more rapidly than the vocabulary parameter. Interestingly, many mainstream large language models assign fewer parameters to the vocabulary than what would be optimal. However, there is a trend towards larger vocabularies, as seen with Llama 3 increasing its vocabulary size to 128,000 from Llama 2's 32,000. Despite this, scaling the training data remains crucial, and addressing data scarcity should be a priority for future research. To validate our predictions, we train models with a specific non-vocabulary parameter under a compute optimal training budget and evaluate their performance. We compare a baseline model using a common vocabulary size of 32,000 with another model that uses the optimal vocabulary size predicted by our third approach. Our results demonstrate that the model configured according to our vocabulary predictions performs better across various downstream tasks, confirming that our predictions are effective at scale. Section Summary. In this section, we propose a parametric approach to predict the optimal vocabulary size by directly modeling the loss based on non-vocabulary parameters, and training data, allowing us to find the minimum loss configuration. Our findings indicate that mainstream LLMs often underestimate the necessary vocabulary size, and our predictions demonstrate improved performance in downstream tasks when using the optimally allocated vocabulary parameters. Section: Experiments with scarce and excessive training data. In this section, we explore experiments involving both limited and excessive training data. Our earlier experiments concentrated on scenarios where the main limitation is the compute budget for training, and we aim to allocate this budget effectively between model parameters and training data. This is a common approach in studies of scaling laws. However, in practical situations, we often encounter a lack of data, which we refer to as data-constrained environments. This can lead us to train models in a less than optimal way, or we might have an abundance of data that allows us to train a smaller, more cost-effective model. To test whether our approach 3 can address these real-world situations, we compared a model with a vocabulary size of 32,000 to another model with an optimal vocabulary size predicted by approach 3. Our findings, as shown in the accompanying table, indicate that our predictions lead to improved model performance simply by adjusting the vocabulary size within different compute budgets. In our analysis, we also examined how the optimal vocabulary size changes with varying amounts of training data while keeping other parameters constant. We tested vocabulary sizes of 8,000, 10,000, 16,000, 24,000, 32,000, and 48,000. For instance, when we have 302 million non-vocabulary parameters and data is limited, we observed that the optimal vocabulary size tends to decrease, moving from 16,000 to 10,000. This adjustment helps to avoid overfitting. On the other hand, when we train with excessive data, such as in the case of Llama 3 to 8b, which uses significantly more training tokens than what is optimal for its compute budget, the optimal vocabulary size increases, shifting from 16,000 to 24,000. It's important to note that our focus here is strictly on optimizing compute resources for training. Additionally, we recognize that increasing vocabulary size also raises the computational demands during inference. Therefore, we suggest using the optimal vocabulary size that corresponds to a given number of non-vocabulary parameters, assuming that training data is allocated effectively, even in cases where overtraining might happen. Next, we discuss large language models, LLMs. The transformer architecture has shown to be highly scalable, consistently improving performance and leading to the development of various large language models. By training these models to predict the next tokens in a sequence, they gain a profound understanding of language, enabling them to perform a wide range of language tasks right after pre-training. These tasks include code generation, mathematical reasoning, and question answering, among others. In our research, we pre-train large language models from scratch using English text and focus on their training loss and performance on common tasks afterward. We also delve into scaling laws, which aim to create a predictive framework for the best allocation of compute resources to enhance model performance. These laws have been examined not only for language models but also for diffusion models, visual auto-regressive modeling, and contrastive language image learning. For language models, it has been shown that performance improves as a power law with increased compute allocated to both parameters and data. It is suggested that compute should be allocated equally between parameters and data. Other studies have looked into predicting various attributes, such as downstream performance and inference time, while some have predicted the expected benefits and optimal allocation under data constraints. However, across these studies, vocabulary size has often been overlooked, with some focusing solely on non-embedding parameters. Our work emphasizes the significant role of vocabulary in scaling large language models. Through our predictive frameworks for determining the optimal vocabulary size, we hope to encourage future research to give more attention to this aspect. We also examine the vocabulary in language models, which plays a crucial role in their performance. A larger vocabulary allows for a broader coverage of words, thereby reducing the chances of encountering out-of-vocabulary cases. Research indicates that larger vocabularies are better at capturing the true statistical distribution of language. Additionally, expanding vocabulary in multilingual models enhances performance, particularly for languages with fewer resources. However, larger vocabularies can increase computational demands during both training and generation phases. It has been noted that low-frequency words may not have enough instances in the training data, leading to inadequate information for creating robust representations if the vocabulary is excessively large. Our work addresses this underexplored area: how to optimally allocate vocabulary size. Lastly, we touch on byte-level language models, which have been investigated recently. These models offer benefits in terms of decoding efficiency and robustness to noise compared to token-level models. However, they are typically limited to fewer than 1 billion parameters and have not been effectively scaled up. Our scaling laws suggest that the restricted vocabulary size, which is 256 in byte-level models, may hinder their performance, especially in larger models. This insight provides a possible explanation for the difficulties in scaling byte-level models and suggests that successful scaling of language models may require proportional increases in vocabulary size.